Hello everyone, welcome to Design Considerations for Dual Band Wi-Fi. In this webinar, we're going to cover some of the general design concepts, some ways that you can design a high-performing, high-throughput webinar with dual band supporting both the 2.4 and the 5 gigahertz band. My name is Joel, and I take care of the majority of training and support here at MetaGeek. If you ever need to contact us, feel free to go to support.metageek.com and open up a support ticket. You'll be put in touch with us immediately. That's usually the fastest way to get a hold of us. Faster yet might be through Twitter, especially off hours. If you have a quick question about Wi-Fi or one of our tools in general, or if you just like to strike up a conversation, feel free to tweet me at Fuel Cell Wi-Fi. More than happy to talk to you there, and we have a really great community going on Twitter of wireless LAN professionals pretty much everywhere. They all seem to congregate on Twitter. It's a great place to go if you want to learn more about Wi-Fi in general. Now, just a couple of quick housekeeping items. If you have a question, feel free to use the question tool throughout the course of this webinar. Be more than happy to answer any questions that pertain directly to the content of the webinar. If you have a question that I don't quite have time to answer or would rather answer off webinar, I'll direct you to open up a support ticket and ask me through that method. Also, if you have any audio or video problems, be sure to let me know. I am using a microphone right now. If the audio seems like I'm instead using the audio that's built into my MacBook on accident, be sure to let me know. So just let me know if we run into any issues, and I will make an effort to correct those for you. So let's go ahead and get started. The first thing I'd like to talk about is the dual band nature of Wi-Fi. And if you've taken a previous MetaGeek webinar, you're probably going to be pretty familiar with this slide and this concept. But for those of you that are attending this webinar for the first time, this is some really important stuff to understand no matter which MetaGeek product you're working on or what Wi-Fi technologies you're using. Knowing the differences between 2.4 and 5 gigahertz are absolutely essential. 2.4 gigahertz emerged back in 1997 when the first 802.11 standard was introduced. And 802.11 was introduced to unify communications between barcode scanners in warehouses. Often it's called 802.11 prime. We don't want to say 802.11x because that could be confused for a wildcard. So most people call the original standard 802.11 prime. Now, 2.4 gigahertz has a fairly long wavelength, and so we see a pretty good range with it, about 300 feet. And back when we were using this technology for barcode scanners in warehouses, that good range worked pretty well, even though we had a pretty limited throughput of about 1 or 2 megabits per second. We had pretty slow throughput. In 1999, the 5 gigahertz band was introduced with 802.11a. Now, 802.11a had a maximum throughput of 54 megabits per second. And at the same time, 802.11b was introduced with a max data rate of 11 megabits per second. So it was quite a bit slower. 802.11b was in the 2.4 gigahertz band, so it was fully backwards compatible with the older equipment, whereas 802.11a was in a brand new slice of spectrum and which required new radios. And they were a bit more expensive to build, and the range wasn't as good. They only went about 90 feet. So the radios were a bit more expensive to make, the range wasn't as good, and it never really caught on. 802.11a did not end up being nearly as popular as 802.11b. And we're feeling the results of that today. Because of the adoption of 802.11b, we see that the 2.4 gigahertz band is universally compatible. There is a lot of stuff that works in the 2.4 gigahertz band. The 5 gigahertz band, on the other hand, has limited compatibility. We're still seeing a lot of devices that don't support 5 gigahertz. And the way to tell is that if you look at the box or the specifications for a Wi-Fi adapter, if it says BGN, those are all 2.4 gigahertz standards. Now, yes, 802.11n does work in the 2.4 and the 5 gigahertz band, but just because it says N does not mean that it supports 5 gigahertz. The way to tell is if it says 802.11a or 802.11ac. If you see that, then you know that it's a dual band device that supports both the 2.4 and the 5 gigahertz band. The compatibility is limited, but this is getting better and better over time. For example, in 2012, I bought a 7-inch Android tablet called the Nexus 7. It was $199. It was an excellent little tablet, but the one thing that I didn't like about it is it was BGN only. It did not have a 5 gigahertz adapter on board. Now, in 2013, Google refreshed the tablet. The new model supported A BGN. It was a good dual band device that supported both the 2.4 and the 5 gigahertz band. And I have one of each sitting here on my desk right now that we're going to use in a little while to do some comparisons between the 2.4 and the 5 gigahertz bands. Now, since the 2.4 gigahertz band is so popular, since it's been around for so long now, it's highly congested with Wi-Fi. Pretty much everything defaults to the 2.4 gigahertz band because that's what everything supports. Now, you will see some devices out there that support the 5 gigahertz band, like every iPhone since the iPhone 5 has a dual band adapter on board. Even my old 2009 Mac Mini has a dual band adapter. It's got 802.11a BGN support, so it supports both bands. But we still see a lot of inexpensive Windows tablets and Windows laptops and Android tablets and Android phones as well that only support the 2.4 gigahertz band. For example, the Moto E is a phone by Motorola. It's $120 off contract. It's BGN only. That's part of the price that you pay for the exceptionally low price for that device. Same goes for the Moto G and a few other budget devices out there are only going to support the 2.4 gigahertz band. And that means that it's highly congested with Wi-Fi. There's a lot of Wi-Fi devices that operate there. Now, 2.4 gigahertz is wide open spectrum. It's unlicensed spectrum, which means anybody can operate a device there. And so it's plagued with non-Wi-Fi interference. We see a lot of non-Wi-Fi devices there as well. And it's got a pretty good range as well, so that makes it very attractive for things like baby monitors and microwave ovens and cordless phones and wireless video cameras. And the list goes on and on and on of all these devices that support or that operate in the 2.4 gigahertz band. You can run stuff in the 5 gigahertz band as well, but the range isn't as good, so a lot of consumer electronics don't end up utilizing the 5 gigahertz band. And perhaps the worst problem with the 2.4 gigahertz band is that it has only 3 non-overlapping channels. There are only 3 channels that don't overlap, whereas the 5 gigahertz band has 24 non-overlapping channels. Just look at the difference in size between these two bands. The 5 gigahertz has a lot more room, a lot more space to support a lot more devices, and so we need to be sure that we're utilizing that. Now, you might be wondering, well, hang on a second, Joel. You're saying there's only 3 channels there's only 3 channels in the 2.4 gigahertz band? What are you talking about? I'm in the U.S. and I only have 11, and my friend lives over in the U.K. and he's got 13. What do you mean that there's only 3 non-overlapping channels? Well, here's the thing. Each Wi-Fi channel is 20 megahertz wide. Each Wi-Fi channel is 20 megahertz wide. And between the channels, there's only 5 megahertz of separation between the centers of the channels. And so when you do some math really quick, you realize that each Wi-Fi channel has the potential to overlap the adjacent channel by about 75%. They all partially overlap with the exceptions of channels 1, 6, and 11. Those are the only 3 channels that don't overlap. And when two channels partially overlap, when 2 networks partially overlap, some bad things happen, and we're going to talk about that here in just a few minutes. So really, the end result is that in the United States, we really only have 3 non-overlapping channels to work with, and in other parts of the world, we have 4 non-overlapping channels to work with. But for the sake of this webinar, I'm just going to use 1, 6, and 11. You know what I mean. Now, the next thing to keep in mind about Wi-Fi is that it is half duplex. Now, many of us are familiar with Ethernet. We've all pulled and connected an Ethernet cable in our day. And an Ethernet cable has multiple twisted pairs of copper in the same cable. And that allows us to send traffic in 2 directions at the same time down one Ethernet cable. If you have a computer talking to a switch, the switch can send the computer information and the computer can send the switch information at the same time. It's like a 2-lane highway. Wi-Fi is a little bit different though. Wi-Fi is a lot more like a human conversation, a conversation between 2 people. If you're talking and somebody else starts talking in the middle of you talking, you're going to interrupt each other. You can't both talk at the same time. You both can't talk and understand each other at the same time. Wi-Fi is the exact same way. If this access point and this laptop were to try to talk at the same time, they would just garble each other out. They would cancel each other out. Only one device can talk on a channel at a time. So here's what the conversation typically looks like. In this example, we've got a router who needs to send, or an access point, depending on what kind of environment you're in, that needs to send some information to this laptop. And so it's going to transmit that data to the laptop. And upon receiving that, the laptop is going to go, yep, check, I received that data. And it's going to reply with an acknowledgement. It's going to say, hey, Hey, access point, yep, I received that data. Now, if something bad happens along the way, let's say that the access point sends the data and then somebody turns on a microwave oven at the exact moment and it just gets garbled and so it never gets there. The router's going to wait and it's never going to hear the acknowledgement. It will never hear a reply from the laptop. And so it'll start wondering after a while, okay, well, did it ever receive it? And so eventually it's going to try to resend that frame and it'll try to retransmit that frame until it gets through and it gets checked by the laptop and an acknowledgement is sent. Now, this happens either way. This can happen in the opposite direction as well. It doesn't matter whether it's a laptop or a phone or an access point or a router, does not matter. So every device on a channel has to take turns talking. Only one can talk at a time. And the more devices you put on a channel, the smaller and smaller everyone's opportunities to talk get. It's like a dinner table conversation. If you're at a small dinner table, there's only 4 people at the table, everybody gets a pretty big slice of time to talk, right? There's plenty of opportunities for everyone to say what they want to say. But when you get 30 people at a table, nobody really gets a good opportunity to talk. There's going to be so many people wanting to say something that not everybody's going to get to talk as much as they would like to. With Wi-Fi, it's the exact same way. Now, in this example, I've got a device that's transmitting to this access point. They're having a conversation right now, and we're sending some data frames to the access point. All these other devices are going to be quiet and wait for their turn to talk because only one device can talk at a time. And the more devices you put on a channel, the smaller and smaller everyone's opportunities to transmit gets. It's kind of like pie. If you were to go to a party and there's 8 people at the party and you take a pie, everybody gets a pretty big slice of pie. But if you take a pie to a party and there's 30 people at the party, everybody's going to get a tiny slice of pie. If somebody offered me a 30th of a pie, I'd probably say no thanks. That's not even worth it. It's the exact same way with Wi-Fi. The other thing that we have to think about is slow talkers. Slow talkers can cause us a lot of problems. If we have a device that's talking at 54 megabits per second, that's a nice, fast 802.11g data rate. But then we've got this device over here, and he's kind of on the edge of the coverage area. So he's having trouble connecting to the access point. He's having trouble being heard by the access point. So he's going to slow down and use an older, slower data rate so that he can be heard better. So he's fallen all the way back to 1 megabit per second. That's 54 times slower than the device that's talking at 54 megabits per second. This device is a lot like the slow kid in the back of the classroom. We all know who I'm talking about. The slow kid in the back of the classroom is the one who raises their hand, and that's when you put your hand on your face and you go, oh, this is going to take a while, because that person takes a very long time to ask questions, and the whole class has to be quiet and wait for him to finish talking. So we have to be careful that we don't put too many devices on the channel, and we have to be careful that we don't let anyone talk too slowly because they can eat up all the time that we have to talk. So let's talk about different types of interference in the 2.4 gigahertz band. We, for the past few minutes, have been talking about co-channel interference. This is where devices are on the same channel, and to be honest, it works pretty well. As long as there aren't too many devices on the channel, and as long as no one's talking slowly, those devices are going to politely take turns talking. They're going to compete for time to talk, and that's going to work fairly well. The one that doesn't work is adjacent channel interference, and that's where we're on partially overlapping channels. We looked at that earlier. Let's say that we had a wireless network on channel 4, and we also have a wireless network on channel 5. That's an adjacent channel. It's right next door, so it's going to overlap by about 75%. And then let's say that we have a wireless network on channel 6. That overlaps with the first 2 as well. So all 3 of these networks are partially overlapping with each other. They're not on the same channel, but they're on adjacent channels, so they cause interference with each other. Instead of politely taking turns talking, they're just going to yell over each other. They're going to interrupt each other, and then everyone's going to have to resend their frames because they got interrupted. It's going to cause retries, and it's going to take more time. This is one of the easiest types of interference to avoid. If everybody used channels 1, 6, and 11, 2.4 gigahertz would be a much better place for everyone. Then there's non-Wi-Fi interference. We have to deal with this as well. This comes from things like microwave ovens and analog video cameras and cordless phones. Non-802.11 devices are also competing for time to talk, and they typically aren't nearly as polite. Now in the 5 gigahertz band, you'll notice that we're actually missing a type of interference here. What happened to it? Well, we don't have any adjacent channel interference in the 5 gigahertz band because none of the channels partially overlap. all of the 20 megahertz wide channels don't overlap. So we still have to deal with co-channel interference. And sometimes we have to deal with non-Wi-Fi interference, but it's a bit more rare. So the 5 gigahertz band is going to work a lot better in general since we've dropped adjacent channel interference. So let's take a quick break and take a look at some different tools that we might use for some different jobs. And we're just going to look at some MetaGeek tools first. First, adjacent channel interference, where we've got two networks that are partially overlapping. Insider is a great tool to discover these and get rid of them. It's a Wi-Fi scanner that shows you where all your wireless networks are, what channels they're on, that is, and shows you how they overlap with each other. So you can make sure everybody's on some good channels like 1, 6, and 11. For non-Wi-Fi interference, Channelizer and the special hardware that goes with it, which is called Wi-Spy, can show you all the raw radio frequency activity around you. So you can see the microwave ovens and the cordless phones and the wireless video cameras that might be causing trouble. You can also see how busy each channel too. And finally, to troubleshoot co-channel interference issues where devices are sharing a channel, you need a packet analysis tool like IPA, which stands for I Packet Analysis. It's also named after beer because our developers, all of them, love beer. So this is a great tool for checking out to see what's going on a specific channel, and we're going to dive into that really in depth. The fourth type of tool that I wanted to point out, this isn't a tool that MetaGeek makes, but we do resell some of these, are a site survey or RF planning tool. So these tools, typically, not all of them, but typically they have two modes. They have an RF planning mode where you can take a floor plan. So what I've done, this is the MetaGeek office right here. And so what I've done is I've gone through the MetaGeek office and I've told the software where the walls are. So I uploaded a floor plan and then I just drew in wall types on top of it. I said, oh, this is a divider, this is a divider, this is drywall, this is a door. And so now it knows what the floor plan looks like. And then I dropped in some virtual access points. I dropped in virtual access points so it knows where they are. And then it calculates out approximately what the coverage looks like. And you can use a tool like this to effectively plan a good wireless network. Now, it's not going to be absolutely perfect. In fact, it's only going to give you a rough idea of what the real world looks like. But it can help give you a good idea of where you should probably place your access points for optimal performance. And another component of this is the site survey component of this tool. Often it's built into the same tool. With the site survey tool, you can walk around in that floor plan, and as you walk, you're going to walk around all over the place. You'll tell the software whenever you turn a corner, and then the software will gather data from your Wi-Fi adapter on your computer, and it will use that to determine just what the coverage looks like. So you can get a real-world look at exactly what the coverage looks like. You can make sure that your cells are arranged properly. You can make sure that everybody has coverage. And you can even use it to locate access points. So pretty much every tool out there comes with the site survey component built in. And then the RF planning component depends on which tool you buy. Some of them include that component and some of them don't. So let's take a look at 2.4 gigahertz and how it performs. Earlier, I mentioned our packet analysis tool, which is called IPA, which stands for I Packet Analysis. And two reasons for that. First off, I mentioned beer. Second, is that it uses these multi-layered pie charts to give you a visual representation as to what's going on from a packet analysis standpoint. And it also looks like an eye. So we kind of had an eyeball. So really, we kind of had three good reasons to do that. So I'm going to explain exactly what these charts and graphs mean in a minute. But first, let's just look at some numbers from this tool. So what we did here is we took a dual band Android device. It's an older one. It's a Google Galaxy Nexus, but it checks out. It's got a dual band adapter on board. And so that device, we connected it to the 2.4 gigahertz radio on a dual band enterprise grade access point. And then we did what everybody did. We streamed a YouTube video. So we did that, and then we stopped the capture and we opened up the capture to see what happened. So I've pulled out some data for you here where we can read it a little bit easier. And so we can see that during this packet capture on this 2.4 gigahertz channel, while we were streaming this video, we saw 27 other SSIDs, so 27 other networks on this channel. We saw 311 other clients, so 311 clients or devices on this channel in total. For the entire channel, our retry rate was 39%. So 39% of the time, we had to repeat ourselves. We had to say the same thing again to get the point across. Now, for the individual client for our Android phone, we see that we used a data rate of 11 megabits per second. That's an 802.11b data rate. That came out in 1999. We were using that data rate. And we can see that our retry rate for this device was 37%. So we spent the majority of our time talking slow and repeating ourselves. It wasn't an efficient conversation at all. So then we did the exact same thing in the 5 gigahertz band. In the 5 gigahertz band, here's what we saw. We saw 2 other SSIDs. So instead of 27, we saw 2. And instead of 311 clients, we only saw 43. It was much quieter. And instead of a retry rate of 39%, we only saw a retry rate of 9%. So a whole 30% less. We had to repeat ourselves less often. And instead of using a slow data rate like 11 megabits per second, we used a nice, fast 802.11g data rate of 51 megabits per second. We got on the channel, we said what we needed to say really quickly, and we got off the channel without having to repeat ourselves. It performed much, much better. So, screenshots are nice and all, but what if we actually did this right now? Let's take a quick break, and let's actually take a look at what this looks like in the real world at MetaGeek right now. So give me just a second to set up my packet capture. So we'll start with the 2.4 gigahertz client first. It's simply connected to the MetaGeek network right now. And this is a 2012 Nexus 7, which is the single band device I mentioned earlier. So now I've switched over to my Windows virtual machine, and I've connected an AirPCAP NX, which is a special packet capture device by Riverbed, and I'm starting up IPA now. And so I'm going to use Insider for Android, and I'm going to see which channel I'm connected to right now. I am on either 1 or 11. I am on channel 11 right now with this device. Now, earlier, I'd had some trouble with my 2013 was also connected to the 2.4 gigahertz band. I hope we don't have that same problem again. We'll see how it goes. It is a live demo. Worst case scenario, we only get to look at the 2.4 gigahertz band. So I'm going to connect my AirPCAP NX. So I'll just connect that to my virtual machine. You may have noticed I'm on a Mac today. I'm just running this software in a Windows virtual machine, and it works great. It works absolutely awesome. I love it. So, okay, I'm going to start my capture on channel 11. So now we're capturing all the packets that are on channel 11. So now I am going to run a speed test on this channel. We're just going to do a throughput test and see how well it performs. Now, this tablet is getting a little old now, so it takes just a moment for speed test to start up. I do love this tablet though. One of my all-time favorites. So now we're trying to find the server right now. So now we're going to go ahead and start the throughput test. And what you'll notice is you'll probably notice that this number starts climbing a little faster. Yep, there it goes, a little bit quicker than before. So now we have about 13 megabytes worth of data. That's more than enough for me to see what's going on in this channel. So I'm going to hit stop. And so now IPA is going to parse out that packet data to make the navigation really quick later on. This tool was kind of born out of us loving Wireshark. We think Wireshark is awesome. But what we didn't like about Wireshark is that it didn't give you any visual representation. So we built a tool that's fully compatible with Wireshark that gives you awesome representations as to what's going on. So each slice of this multi-layered pie chart gives us shows us how much each wireless network talks. So there's MetaGeek. There's MetaGeek Aurora QA. It's one of our quality assurance guys, access points, unknown. Here's an HP printer. It's out there somewhere. There's a bridal shop that's downstairs. Here's a Motorola device. So we could see exactly how much time all of these networks spent talking. And this is a multi-layered pie chart. The innermost ring is the network as a whole. So MetaGeek has multiple access points on our network. So we could see that here's an access point, and here's an access point, and here's an access point. So we have 3 access points that are on this channel that we can hear. These other 2 are probably a little bit more distant. They're probably a little bit further away. We go the next layer out, and now we're looking at our individual clients. So we can see that there's an LG device. Taylor has an LG Nexus 4, so that's probably his Nexus 4 right there. And this right here, that is my Nexus. That's my Nexus 7. So what I can do here is I can click on this access point, so we can drill down into it. So now we're just looking at this access point, and we can see that my device spent the most time talking. But we can see some interesting facts about it. We can see that the retry rate was 27%, and we can see that the data rate was 50 megabits per second. Not bad, actually. That went pretty well. That's a lot better than I was seeing earlier this morning, perhaps because it's just after lunch here and most people probably aren't using the Wi-Fi right now on all the other networks that are nearby. So we can see that that device actually was pretty successful. We had a 27% retry rate, which is not bad, and a data rate of 50 megabits per second. So pretty good, pretty good. So now what I'm going to do is I'm actually going to check on my 2013 Nexus 7, and let's see which channel it's on. It looks like today it has our infrastructure here, for whatever reason, the signal strength in my office is not that good, so it looks like it's kicked me over to the 2.4 gigahertz band, but that's okay. I just wanted you to get a good look at what this tool looks like, and I think that was a pretty good example. So let's go ahead and jump back into our slides now, and let's talk about some ways that you can design a proper dual band wireless network. So there's some goals that we want to achieve when we're designing a good dual band wireless network. First off, we want to eliminate adjacent channel interference. That causes retries, right? We have to retry if we have partially overlapping channels. So we really want to eliminate adjacent channel interference in our network design. Next, we want to minimize co-channel interference. We want to make sure that devices don't have to take turns talking all the time. We want to try to keep those channels as clear and free as possible. And we want to provide a 2.4 gigahertz compatibility. We want to give those older devices like my 2012 Nexus 7, we want it to be able to connect to the network still. But we also want to provide a nice, fast 5 gigahertz network for our newer devices to connect to. Whether it's 802.11n or 802.11ac, it doesn't matter. We want those devices to be able to utilize the faster and better 5 gigahertz band. So step number one, and this is a pretty easy step, sort of, is to eliminate adjacent channel interference. No more of this stuff. We don't want to be on channels that are partially overlapping. Here's the thing, neighbors. The problem that we have here at MetaGeek is that we have a lot of neighbors. We're in a multi-tenant building. We're on the 5th floor of a 7-story building, and there are other tenants above and below us. Some of them are on channel 3, some of them are on channel 5, some of them are on channel 9. And so we suffer from a lot of adjacent channel interference here at MetaGeek because of the neighbors. It's something that we just can't quite get away from. In a perfect world, we would all be using non-overlapping channels. We'd all use channels 1, 6, and 11. And if you're working on a larger network that covers a larger geographical area, it's totally possible for you to be able to deploy everything on channels 1, 6, and 11. With the occasion of the Verizon MiFi hotspot that comes wandering through on channel 3, we can usually get everything on channels 1, 6, and 11. And if you're in other parts of the world, you can use channels 1, 5, 9, and 13 for a 4-channel non-overlapping scheme. The next thing that we need to do is minimize co-channel interference. And unfortunately, we have to do another list because there's several things that we can do to minimize co-channel interference. First off, we can use small cells. We can also use dual band access points. And we can deploy a good channel plan, and we can make sure that everyone has good coverage. So let's go ahead and investigate each one of these things so you can see exactly what I mean. First off, we want to eliminate these large cells if we can. The problem with a large coverage cell, like you might see with a 2.4 gigahertz only access point or a quote-unquote long-range access point, is that we have a whole bunch of devices that are all sharing the same channel. Maybe this is channel 1 and it's covering a large area, so all of these devices are on the same channel and they're all going to have to take turns talking. Only one of these devices can talk at a time because they're all on the exact same channel, all taking turns. We want to avoid that. And one way that we can avoid that is by using small coverage cells. We can use little cells to divide everything up and divide them up all onto different channels. So we have our channel 6 and our channel 11 and our channel 1. These are all different channels. All 3 of these are different channels, and so they do not have to take turns talking. And now we're down to about 3 devices on each channel, so hardly anyone's having to take turns talking. Now, we only have 3 non-overlapping channels to work with, so we might have to reuse our channels. And when we do that, we're just going to keep those same channels as far away from each other as possible, so that way they don't have to take turns. We don't want to put 2 channel 1s right next to each other, because then they'll have to take turns talking, and we don't want to do that. Small cells divide devices up into different channels, which means less co-channel interference. It fixes that problem. The next thing that we can do is deploy dual band access points. We get a bonus channel out of that because now instead of just offering channel 1, now we're offering channel 1 and channel 36. So all of our 5 gigahertz devices can go to channel 36 and all of our single band devices can go to channel 1. Now typically, historically, channel 1 still ends up being more crowded because more devices support that band. So it's not going to perform as well, but it at least gets us some compatibility. I talked to somebody who deployed Wi-Fi at a large event, and their 5 gigahertz network worked very well actually. But the problem about this event was a lot of people brought in hotspots, like a Verizon MiFi hotspot, or they were using a hotspot mode on their phone so they could use their laptop on the internet while they were at this event. And the problem is all those devices clogged up the 2.4 gigahertz band. So 2.4 gigahertz did not perform very well. They did the best they could, but it didn't perform super well. Whereas the 5 gigahertz band performed really well because there was no adjacent channel interference and there were no hotspots in the 5 gigahertz band, and it performed much better because of that. A dual band access point gives you a bonus channel. You get 2 channels at the same time with 1 dual band access point. When we're thinking about deploying more than 3 access points, we need to think about channel reuse a little bit. And I just touched on this earlier. We want to keep our same channel access points as far away from each other as possible. And so you often see access points getting deployed in a pattern much like this. Now, keep in mind that radio frequency does not travel in a perfect circle like this. It's typically a much more erratic shape, and so it requires some finesse in a site survey or RF planning tool to really get this right. But what you want to do is make sure that your channel 1s and your channel 11s and your channel 6s just can't see each other. You don't want them to be able to see each other. You want them distance from each other as much as possible, and you want to kind of keep those separate if possible. In the 5 gigahertz band, it's a lot easier. Remember, we have 24 non-overlapping channels to work with. Now, some of those are the DFS channels, the dynamic frequency selection channels. Those channels are a bit trickier to use because the access points and the clients have to support being able to avoid Doppler weather radar on those channels. If they sense Doppler weather radar from an airport, which is an extremely critical technology for landing airplanes safely, then they need to be able to move away from those channels and not cause interference. So we don't have quite all 24 non-overlapping channels to work with, but we still have a lot more space. And you can see here in this channel plan, I actually ran out of colors. I ran out of colors to use before I ran out of channels. So we have a lot more channels to work with. And one thing I forgot to mention about these dual band access points. You remember how the 2.4 gigahertz band travels a lot further. What I see a lot of people doing is turning down the output power on the 2.4 gigahertz band to make it match the 5 gigahertz band, and then deploying more access points to cover everything nice and evenly. Speaking of range, let's talk about it for just a minute. So this is a screenshot of Ekahau Site Survey. This tool is both a site survey tool and an RF planning tool. It's got a very good RF planner, and I've met the Ekahau guys. They are awesome. We absolutely love Ekahau. We think this is a fantastic tool. So what I've done with this tool is I've taken a floor plan and I've drawn in my wall types. Just like I explained earlier, we said, hey, this is a brick wall, this is a brick wall, this is drywall, this is also drywall. And so the tool knows approximately what the floor plan looks like. And then I've placed a virtual access point in here. And I dropped in a single band 2.4 gigahertz only access point to see what the coverage would look like. So here's what I found. The further that we move away from the access point, the further down our data rate goes. We might go from a nice fast data rate, like maybe we get 150 megabits per second in here, but by the time we're out here in this red section, we're only getting about 11 to 1 megabit per second. We're getting pretty bad data rates out here. And the problem with this is that we have got one access point covering this entire half of the building. That could be 50 devices for all we know. On a busy day when there's a lot of devices in here, we could have a lot of devices sharing the same channel, and we want to avoid that. The other problem, the thing that compounds this issue even more, is that out here, we're going to be using a pretty slow data rate, like 1 megabit per second, to be heard by the access point. So even though we have a greater indoor range, they say that indoor range is typically a good thing, right? Well, in this case, no, not really, because we've got a lot of areas here that get coverage, but very poor coverage where devices talk slowly and keep all the other devices from being to say what they need to say. If we drop a 5 gigahertz access point in here, we still see kind of the same problem. we see that there's a lot of spaces here where we're not going to see good coverage. Now, the slowest data rate that we can see in the 5 gigahertz is 6 megabits per second. That's the minimum data rate that we have available in the 5 gigahertz band. So it's never going to get quite as crawling slow, but we'll still have problems, and it just doesn't cover as much space. Now, the lower indoor range is typically a bad thing, right? Or is it? The fact is that 5 gigahertz is kind of like a quiet and polite neighbor. Have you ever had a neighbor that was really noisy that you could hear really well? In the 2.4 gigahertz band, you can hear your neighbors very well, but in the 5 gigahertz band, it doesn't go as far, so you can't hear them as well, which means your network can perform faster and you don't have to share it with other people. So here's how we deploy an effective dual band network on this same floor plan. What we've done is we've dropped a lot more access points in here with smaller coverage areas. And each one of these access points is a dual band access point supporting both the 2.4 and the 5 gigahertz band, each and every one. We've kept our same channel access points as far away from each other as possible. So that way our channel 1s and our channel 6s and our channel 11s, they can all be as far away from each other as possible to minimize co-channel interference. We've also split all of our devices up into smaller cells, so they're closer to the access point, so they'll be able to communicate faster, and they won't have to share it with nearly as many other devices. We've also used channels 1, 6, and 11 only, so we have eliminated adjacent channel interference. We've minimized the co-channel interference, and because we've deployed dual band, we have doubled our potential available wireless bandwidth. Providing a network on both channel 1 and channel 36 gives us a bonus channel. We have 2 channels to work with. We've provided compatibility for the 802.11bgn devices, those older devices, like those older Windows laptops, and that the employee that has a Moto G with what they picked up for $180 off contract. And then we've also provided 5 gigahertz support for our 802.11n or 802.11ac clients so they can have better performance. And because of all this, we've lowered our retry rates and we have lowered impact from interference. We have successfully deployed a good dual band wireless network. If you'd like to try out IPA, that's the packet analysis tool that we used earlier, there is a free 7-day trial on our website. Go to metageek.com/downloads. This is supposed to be .com. Ignore that. We just changed our domain to .com, so I don't think the .net will go anywhere now. But if you go to metageek.com/downloads, it's there. You can download it, and then when you install the software, there is a request a trial button where you can request to have a trial key sent to you, and we'll send you that key in just seconds. As for pricing for IPA, this packet capture tool, you can get your packet captures from an enterprise-grade access point or from a Mac. There's a tool built into Mac where you can get those natively from a Mac with minimal hassle, or from Linux, you can pick it up for $4.99. If you're using Windows, Windows has some pretty big limitations in how it lets us get our packet captures. We can't do packet capture with a normal Wi-Fi adapter because it leaves out some important information. So we use a tool called the AirPCAP NX by Riverbed. And so we give you $50 off if you buy IPA and an AirPCAP NX together. The AirPCAP NX is natively supported in IPA and Wireshark, captures full 802.11n. It also will do some 802.11ac airtime calculations because we can hear all the management overhead. So we can do most 802.11ac airtime calculations. And it's a 2x2 MIMO device, so you can capture multiple spatial streams at the same time with the AirPCAP NX. If you have any questions, feel free to ask now. You can also contact me at support.metageek.com. You can click the Submit a Request button, and to open up a support ticket with us, that'll go almost directly to me, and I'll get back to those questions as quickly as possible. You can also contact me on Twitter if you'd like to talk to me there as well. Thanks for joining our webinar today. Looks like we don't have any questions at this time, so I'll go ahead and end the webinar. Thanks for attending, and have a great day, and we will look forward to seeing you in a future MetaGeek webinar.